Now we'll come to the snake rule. Alright, now how to write it down, just you see, because upon writing only you'll understand it. Alright, so first what you do is that you write it in this way. One is, then leave little bit gap. You can leave 2 lines in your notebook. Two lines you can leave it between the numbers. It will be easy for you. You'll come to know 1s, 2s, 3s, 4s, 5s, 6s, 7s. Now you don't write it 8s, 9s. Because maximum number of shell is 7, because there are 7 periods in a periodic table. It's not that 8, 9, 10 will be going on writing. No, not possible. Now you leave 2 spaces and start from here. 2p straight line. In straight line 3s. Then 3p again straight line. Then 4p. Then 5p. Then 6p straight line. And 7p. We can say that. 2p, 3p, you leave 2 spaces. Then start from, here you started from 1, here you will start from 2. 2, 3, 4, 5, 6, 7. Now again leave 2 spaces. Alright, and you start from here. After SP, D. 3D, 4D, 5D, 6D. We can say that. Again leave 2 spaces. That is nothing but, let me write it here, 5D, 6D. Then it will be, again leave 2 spaces. 4F, 5F. Done. Now I have to join the lines. The snake I have to make it. Alright. Now see here how I am doing it. You start from here. See the direction of the arrows. 1s. Then after 1s, what is that? 2s. Direction of the arrows. Then you start from here. After 2s, 2p. Then 3s. Now from the middle. You can also start. You can say, sir, I will draw from the middle. Okay. If you draw from the middle, then what will happen? You know. This. What is the use, you say me, by drawing in this way? Any use is there? No. So hence directly you can do what you can say, that is 2s, then after that you will come to 2p, then 3s, then from the middle, now all from the middle, then 3p, 4s, 3d, for that reason I asked you to leave the line in the middle, 4p, then 5s, again from the middle, 4d, 5p, 6s. Then from the middle, 4f, 5d, 6p, 7s. Again from the middle, you land here. Alright, so see the arrows. Let me draw the arrows. You can see. Now is check here. 1s and after that 2s. See the arrows. Direction 2p. Then 3s. Then after the direction you see 3p. Then 4s. Then after that 3d. Then 4p. That means what I have to do is that when you write the electronic configuration. After this just now I will teach you electronic configuration. After 1s you will be writing 2s. Then after that 2p. You have seen the increasing order of energy. 2s, then 2p, then 3s, then 3p, then 4s. Then after that, after 4s it is not 5s. It is 3d. Then 4p, then 5s. Then after that it is not 6s. No, 4D, 5P, 6s. In this way it goes on. So just it takes few seconds or a minute, we can say that, to write this particular snake rule. Once or twice you practice, you will be able to do it. In the exams also you can write it down in the rough paper. This one, 1s, 2s, in this way write it down as I have written it and practice it. Alright, you will be able to remember the electronic configuration, how to write it down. You will be able to fill up. Alright, because you have to remember it, the increasing order of energy of the subshells. So how to remember it? In this way with the help of snake rule you can remember it. Okay. Now, this is snake rule. Now we will come to electronic configuration. How to fill up the electronic configuration. So, electronic configuration, the general formula is, electronic configuration is NLX. N is the principal quantum number, we have seen it. L is the azimuthal quantum number, SPDF. And X is the number of electrons in that particular subshell. So you have to remember it, you cannot exceed the maximum number of electrons in a particular subshell. For example, S subshell can maximum it can accommodate 2, P subshell 6, D subshell 10, 4 different subshell, F subshell 14 in this way. So you have to remember it. S is 2 maximum, P is 6, D is 10, F is 14. Alright, you cannot write like 2S 3, you cannot write, or that is 4P7. No, you can't write. It is not possible. You can write 2S1. You can write 4P5, 4P4. Minimum value, of course, you can write, but you cannot exceed the maximum one. Got it? Clear? That you need to remember. So N is the principal quantum number, L is the azimuthal already you have seen it, na? NL we have already seen it, na? That is 1s, 2s, 2p, 3s, they are the NL. Now comes your X. X is nothing but is your number of electrons which you have to write as a superscript over L. Got it? Let me write it one and show it to you. For example, for oxygen 8. So 8 means 1s2 maximum. After 1s what it comes? 2s2 maximum, again 2. You cannot write here 1s 2s3. It is wrong. It is not possible. Maximum is 2. Then count it. 2 plus 2 is how much? 4. Total is how much it is there? 8. It's number of electrons, na? This number should, total number here of the electron should be equal to 8. So 4 it is. Then after 2s comes what? 2p. Now we have got 4 here. Now p has got maximum capacity of 6 electron. But how much we can accommodate here in case of oxygen? 4. Because 2 plus 2 4, we need another 4. So 4 plus 4 it becomes 8. Done. In this way you need to write the electronic configuration. First you have to remember this one in the increasing order of energy. Next you have to remember the number of electrons in a given, what you can say, subshell. Similarly, let me write for sodium 11. So it is 1s2, 2s2, count it also, number of electron, 2s2 means 2 plus 2 4. Now 2p6, how much you got it? 2 plus 2 4, 6 plus 4 10. One more is there, so it is 3s1. Clear? In this way, 1s, 2s, 2p, 3s. Clear? Now, for example, if you want to write for calcium 20, so 1s2, 2s2, 2p6, 3s2, then 3p6. Are you counting or not? You count it at the same time. 2 plus 2 4, 6 plus 4 10, 10 plus 2 12, 12 plus 6 18. Here 20 is there. So after 3p it is what? 4s. So 4s 2 in this way. Clear? For example, if you want to write it for iron, atomic number 26. Now you can write for anything. You can write it down. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Count it. Up to this it was 20, isn't it? Up to this it was 20. Now 26. So after 4s, what is that? 3d. 3d what? 6. Because d subshell has got maximum capacity of 10 electrons. I written what? 6. Because up to it is 20. You can see I have written it already here. 20. Now more 6 electrons I want. So 3d 6. So you can write the electronic configuration of any atomic number. You will be able to write it down. Any atomic number, whether it is 100 or 90 or 82 or whatever it is, you can write it down in this particular manner. We can say that the electronic configuration of, say, electronic configuration of any particular atom, we can write it down. Okay? Yeah. So next, after this, so we came to understand the electronic configuration, how to write the electronic configuration. Fine. Now you have to also write the electronic configuration of certain atoms. Listen carefully, of certain atoms which is having exceptional electronic configuration. Now why it is exceptional? Achha, before that I have to tell you one particular rule. Before going to that, I have to tell you one particular rule. What is that? Write down. Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. What is that? Write down. Electron pairing in P, D and F. P, D, F. Electron pairing in P, D and F orbitals cannot occur until each orbital of a given subshell contains one electron each or is singly occupied. Until each orbital of a given subshell contains one electron each or is singly occupied. Okay. Now electron pairing in P, D and F orbitals, but rather I should say it is true for F and D only. For P it is rare. That also I say where it is rare. Cannot occur. So when you are filling up the D and F subshell, remember it. When you are filling up the D and F subshell, first all the orbitals has to be singly occupied. How many orbitals are there in D? 5 orbitals, isn't it? dxy, dyz, dxz, dx square, y square and dz square. 5 orbitals are there. Alright, maximum 10 electrons means 5 orbitals. Now, similarly, F subshell has got maximum 14 electrons. In how many orbitals? Half of that, 7. Because each orbital can accommodate maximum 2. Hence, 14 electrons means how many orbitals we'll have? 7 orbitals we can have it. So, when you are filling, listen carefully, when you are filling the D and F subshells, first, each orbital has to be singly occupied. If the number of electron permits, each orbital will be singly occupied. After singly occupied, if an electron is left, then pairing is going to take place. If an electron is left, then only the pairing is going to take place. That is what the Hund's rule of maximum multiplicity said. Means, let me make it more simplified. Let us say we are having D4 electrons. Number of electrons in D subshell is 4. So what you need to draw is that you need to make 5 orbitals. Means here I will draw 5 boxes. Here the box represents orbitals. Listen carefully, the box 1, 2, 3, 4, 5. dxy, dyz, dxz, dx square, y square, dz square will be represented by box here. Now I need to fill this 4 electrons. So how will I fill it? You will say, sir, 1, 2, because each orbital 2, 1, 2, 3, 4. And this? No, it will not be. No, this is wrong. This is wrong. That is what the Hund's rule is saying. That first, we need to fill it singly. 1, 2, 3, 4. This is the correct way of filling. This is the correct way of filling D4. In this way. First, it needs to be singly occupied. If at all any electron is left after being singly occupied, then only the pairing is going to take place. Understood? Alright, what I said. Now, I will tell you the reason also. Don't worry. Suppose there are D7 in D subshell. 7 electrons are there. Again you make, what is that? 5 boxes. You need to make always 5. You cannot have, suppose 4 electrons is there, means 2 boxes I will make it. No. Rest of the boxes will remain vacant, but you have to make it 5. Similarly for P subshell, you have to make it is 3, because P subshell has got maximum 3 orbitals. F subshell, you have to make it 7. Even if the boxes will remain vacant, let it be vacant. That's a vacant orbitals, we'll show it. That's a vacant, that particular one is. But we have to make it. Alright, listen carefully these things. So in this way, D7, how will you fill it up D7? Will it in this way? 1, 2, 3, 4, 5, 6 and 7? No, this is wrong. We are not going to fill it up in this particular manner. We are first going to fill it up singly. 1, 2, 3, 4, 5, 6, 7. Alright, this is 1, this is 2, this is 3 and this is 4. 4th electron. Similarly, this is 1, 2, 3, 4, 5. Alright, 5 electrons are filled up. Now this is your 6th and this is your 7th. Alright, in this way we are going to fill it up. I have numbered it also. Alright, for easier purpose. So in this way we are going to fill it up in this particular manner. First it will be singly occupied, then only the pairing is going to take place. If at all the electron is left, like here it is not left. Okay, fine. Suppose D5 will be there. So one more electron will come here. But D6 means after filling 5, then 6 will come here, as you can see it here. Clear? Now, why? The question is, why it is so? How did he come to know? Hund's rule, how did Hund's come to know about it? See, when you are filling one electron in each orbitals, then you are distributing the energy equally in each orbital. You are distributing the energy equally. When you are distributing the energy equally, then energy is less, stability will be more. Mind it, always energy is inversely proportional to stability. If I give you 2 electrons and 2 electrons, the remaining will be vacant. I am not distributing the energy equally. There I am distributing in 2 orbitals. Here I am distributing in 4 orbitals. Definitely the distribution of energy, which is known as exchange energy, remember it, which is known as exchange energy, is more. Because exchange energy means one electron in one. Alright, exchange, that is called exchange energy is more here. When the exchange energy will be more, then energy which will be remaining, that will be less. When the remaining what? In an atom will be less. And when the remaining energy in an atom will be less, the atom will be more stable. Because always we write the electronic configuration for a stable configuration. Electronic configuration for a stable atom. Alright, and by which we show whether it is stable or unstable or whatever it is. So, hence for that particular purpose, we are going to fill it up in this way. First, each orbital will be singly occupied. Alright, why it will be singly occupied? Because you are distributing the energy equally. When you are filling one electron, you are distributing the energy equally. The exchange energy is more. And hence, the energy which is left out, the remaining, that is less, due to which stability increases. Alright, energy decreases because as exchange energy is more, exchange energy means what? Energy which is released is more, given out is more. Alright, and when the energy which is released is more, so remaining energy will be less. The leftover energy will be less, which is known as the residual energy will be less, and hence it will be more stable in nature. So hence for that particular purpose, Hunt said that he made a rule. For that reason he made a rule. Alright, that first we will singly filled, then after that the pairing is going to take place if at all some electron will be left. Alright, now this is the reason. Now the second reason is that when we are filling it up in this single manner, see now D5, let us say here, let me make it as D5, this one, D5. Alright, so one more here, this is the fifth one. Now it is stable due to symmetry, it becomes symmetrical because all is unpaired. Let us say all are clockwise. All this direction, let us say, is clockwise direction. So all are clockwise. It is being symmetrical. So it is stable due to symmetry, we can say that. Alright, it is symmetrical in nature. It is stable due to symmetry. It is symmetrical, we can say that. Clear? If you say no sir, it is not clockwise, anti-clockwise. Okay. Either you can take clockwise or it is anti-clockwise. All are in the same direction. Alright, so it is stable due to symmetry. So hence, remember that. Listen carefully one sentence. If in case of D subshell and F subshell, if a particular subshell is half filled or fully filled, it is said to be stable electronic configuration. In case of D subshell and F subshell, if a particular subshell of D and F is either half filled or fully filled, it is said to be stable electronic configuration. Now here it is half filled. Now it is not half filled, this is partially filled. Understand the word, understand the English. Here it is half filled. So hence I will say you that is ND5, ND10. See here, N means any principal quantum number. N, any, it can be like 3D5, 4D5, anything it is. So hence I have written N. So ND5, ND10. Similarly, NF7, NF14. This configuration is known as stable electronic configuration. This particular configuration is known as stable electronic configuration, which I was talking to you now about exceptional. You will be seeing I will be using this particular one. Alright, so any atom, if it has got this configuration in the outermost subshell, remember it, outermost subshell, then it is considered to be as stable electronic configuration. It is considered to be as. Alright, if any atom in case of D and F, if it is half filled, like half filled here, and if it is fully filled, then it is considered to be a stable electronic configuration because it is stable due to what? Symmetry. Now the next question comes here, that here the two electrons are there. You can see there, two electrons are there. Now electrons are of similar charges. Now electrons, as they are of similar charges, how the two electrons are present in one particular orbitals, because similar charges are there. We know like charges repels. So they should repel one another. So this electron, first and sixth electron here, second and seventh electron, they should repel one another. Instead of that, how two electrons are able to accommodate a single orbital? How? The answer is very simple. The answer is because even if they are of like charges, but their spin is different. If one is rotating in clockwise direction, other is going to rotate in anti-clockwise. If one is rotating in clockwise, other is going to rotate in anti-clockwise. They will never meet. Then how they will repel? They will never meet. Then how they will repel? We can say that. Clear? So hence, the force of repulsion for that reason is being decreased. Alright, it is being decreased. The force of repulsion, even if they are of same charges, similar charges, like charges, the two electrons. But they are able to accommodate a single orbitals because they are of different spin. Because one is clockwise spin, another is anti-clockwise spin. Due to which they tend to cancel the effect of one another. I have told you in spin quantum number, they tend to cancel the effect of one. What effect? That is the electrostatic charges. They tend to cancel the electrostatic charges of one another. They tend to cancel it. Due to which they are being stable. Hence, they are able to accommodate particular, what you can say, single orbital, even if they are of same charges. I hope you understood this particular thing. Alright, now you have understood how to fill up. in D subshell and F subshell, how to fill it up? First, it will be singly occupied. If at all some electrons will be left, then only the pairing is going to take place. That's it, you have to remember it. Alright, it's not that 1, 2, 3, 4 in this way. No, first 1, 1, 1. Make it a habit of filling it up. Then you will understand it. It becomes easier for you. Alright, make it a habit. Everything depends upon the habit. Once you make it a habit, then it becomes easier. But the reason you need to understand, the concept you need to understand, that why Hans had made this particular rule, we can say that. Now, let us write the electronic configuration where this particular theory is going to help us. Let us write the electronic configuration of chromium, atomic number 24. Now, you will write it in this way, definitely 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So, 2 to 4, 6 4 10, 2 12, 6 18 to 20. So, more 4 I require. So, 3d4. Alright, now 3d4. Now, I am interested only with the outermost subshell. Outermost. I am drawing only for the outermost. Mind it, only for 3d4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 orbitals, I got it. Now 3d4 means 1, 2, 3, 4. Now 1 is vacant. Now I forgot to tell you that if an electron has 1 electron less for being half filled or fully filled, then it's considered to be highly unstable in nature. What I said, if an atom or if any particular, if a subshell, the outermost subshell, outermost only it will have, an atom, if the outermost subshell of an atom has got 1 electron less for being half filled or fully filled, then it's considered to be highly unstable configuration, because it is not symmetrical. It is highly unstable. It will always have a tendency to acquire the, what you can say, stable configuration. That means what I should say, if the electronic configuration is Nd4, Nd9, Nf6, Nf13. See, for half filled it should be Nd5, 1 electron less. For fully filled, Nd10, 1 electron less. For half filled, Nf7, 1 electron less. For fully filled, Nf14, 1 electron less. So 1 electron is only 1 electron, mind it, only 1. Don't say, ask me here, Nd3, Nd8, what will happen, sir? Nothing will happen. It will remain the same only. It will remain the same only. Nothing is going to happen. Here I am talking only about 1 electron less, mind it. If 1 electron is less for being half filled or fully filled, in case of D and F subshell, then it's considered to be highly unstable electronic configuration. Highly unstable electronic configuration. Highly unstable electronic configuration. So, how to attain stability then? Now, this is very important. It will borrow an electron from the penultimate subshell. Penultimate means last but one. From this, it will borrow an electron. It will borrow an electron from the penultimate. Penultimate means last but one, from the penultimate subshell, and it will attain stability. Because this is unstable. How it is unstable? Because it is not stable due to symmetry. It is having a tendency always to attain the stable configuration. 1 electron it will. So hence it will borrow 1 electron from this and it will become stable. Alright, then what is the electronic configuration? Correct electronic configuration. Is this correct? No, this is wrong. This electronic configuration. Then what is correct? The correct is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, not 4s2, 4s1, 3d5. This is correct. So if I ask you to write the electronic configuration of chromium, this you will write it, this not. If you write this, it is wrong. Understood the reason why it is so. Similarly, for copper, 29, we can say. So it is 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 3d9, it should be. Count it, 6, 4, 6, 4, 10, 10 to 12, 6, 18 to 20, 29. But it is again same thing, 9. Not stable, highly unstable. So hence what it will be? 4s1, 3d10. Now this is correct. So there are several elements there. When you write the electronic configuration, you need to see that the outermost subshell should not have 1 electron less for being half filled or fully filled. If it is 2 electron less, no problem. But it should not have 1 electron less for being half filled and fully filled, for D and F subshell. I am talking to you. Then it will borrow an electron from the penultimate subshell and it will become stable. Got it now? Understood? How Hund's rule of maximum multiplicity is playing a role here. Got it? Because you need to understand this. Because why it is not stable? I've said it. Because it is not stable due to symmetry. Alright? Clear? So in this way, you understood how to write the electronic configuration of an atom and also some exceptional electronic configuration. And I told you the reasons also, what are the reasons behind it, that why do we write it down in this way. Alright. So next we'll see some questions.